All right, come on in and hear about the state of SciML. So, this is going to be a retrospective and a roadmap for the SciML organization, right? So, what is the SciML organization? It's this huge organization with tons and tons of Julia packages, and I'm Chris, and I've been working on this for almost 10 years at this point. And so what I really want to do is I want to walk through a lot of what we have done, what we are doing, and where we are going, right? So that way everyone kind of has a good view on what are all the things that are going on in the organization. And dense slide number one, right? Because when I want to say, well, all the things that we're doing in this organization, I think that we're talking about a bigger organization than most people think. Because most people, when I talk to you, you only talk about one part of this organization, right? Because the SciML organization, it is something with, over 100 GitHub repositories, of which many of these repositories, for example, optimization.jl has like 15 packages inside of that one GitHub repository itself. So we're talking about, a good hundreds of packages, and we're actually ready to register about 20 more on ODEs. So there's a lot there. It's over 20,000 GitHub stars across a set of packages. I looked at the last few months to be able to kind of figure out like how many people actually show up, and we have about 100 unique contributors every month, right? So that is, 100 unique people will show up to give us a code change every single month. That's three unique people a day, right? And there's over 20 core maintainers, these are the folks that have the designation of I will ping them when I say, oh, I'm busy, please help me on this given package, right? So there's 20 maintainers spread around many packages. Most of those core maintainers have 3 or 4 packages that they take a hold of. There's a few of us that kind of do 10, and then there's only one crazy enough person to try to look at a few hundred of them. And then there's about 5 to 10 summer students and trainees that we've had every year. We started working with Google Summer of Code all the way back in 2016. And then many of those folks that we had, so 5 to 10 students per year. So we've had, I think and we've also in many years we've had 15 to 20 in different forms. So we've had over 100 students that have been trained up. They become PhD students at the MIT Julia Lab. They become employees at Pumas AI and Julia Hub. And so there's this whole kind of organization of folks that we've developed in terms of people who are maintaining packages, people are contributing, and then people who we've taught everything to, and then they grow up to then have their own research labs now, right? Because again, we're talking about an organization that's now been here for 8 years, and so people who started working on it as a PhD student, they're now actually professors, and they're hiring PhD students who then help maintain some of these packages, right? So I, Chris Rackauckas, am the BDFL, which means that I have, I'm the one person who decides that it's a sane thing to do to be a maintainer on this whole thing and try to make it look as one unifying force. But what that means is that it's going to be very hard to summarize everything here in 30 minutes. In fact, I got through summarizing about 1/4 of the content and 1/4 of the repos and realized I had more than half an hour of content. So everyone will be disappointed because I will leave off some topic that you care about. So, if you're like, oh, I wanted to hear about the state of quasi-Monte-Carlo.jl, or what's not even going to be in the SciML talk? Physics-informed neural networks will actually miss this talk, right? There's way too much in here. So I hope that we're going to have a reoccurring series where we'll have, more one-on-ones to talking about what's going on in different parts of the organization. Because again, this organization at this point is huge, and there's a whole lot of people, and that means that there's a whole lot to talk about. And so what I'll say, at the very beginning, especially if you're there on YouTube, if you want to connect with us, if you want to talk with us, if you want to ask any questions, go to some of our chat channels, right? We have, on Slack, I think the chat channel has 1,500 people. Go ask your questions there. I might still be the one to answer in anyways. Go on LinkedIn, or go to our repositories and just, ask questions through issues. We take all sorts of issues. Even if your issue is not even a bug report, we're happy to respond to you and say, this is not a bug report, so we'll close it, but I'll still chat with you, right? So feel free to get in touch with us in any way, shape, or form that you want to talk about what's going on here. So first question is, what is the SciML open source organization, right? And so there's one way to talk about it where you just say, okay, what's all the stuff that we have, right? And at this point, Again, it's hundreds of Julia packages. And so one way to talk about it is to say, well, we have hundreds of packages, and there's things that include modeling tools, there's numerical solvers, there's analysis tools, there's tools for machine learning, and there's developer tools, right? You can almost think about it as if you took SciPy, and then you said, well, I also want all of MATLAB, and I also want all of JAX, and I also want, well, everything that, if you've heard of Modelica and Simulink, let's just take all of this and make sure that it all works as one giant system. If you wanted all of that at once, that's kind of SciML at this point, right? And so that is a huge footprint as to what we are, but that is what we're aiming to do, right? All the stuff that you do with numerical modeling and simulation, how do we make it so that way it's all one very cohesive, piece that works all together? And so, trying to picture it, what is the organization? I stole a picture from one of the postdocs at MIT and one of the students at MIT, where they created this graph of SciML where they tried to say, this is about what it is. Again, this has about 30 packages up there, so that's only 1/3 of the things there. And even there, you can start to see that, but there are some major themes, right? So there are things like there are numerical equation solving packages, and there's a lot of tools for simulation, which are numerical equation solving on differential equations. There's tools for optimization, analysis, tools for modeling, right? So there's these giant, there are these giant kind of hubs of, these core things that we're trying to do, and then there's a lot of small packages that are trying to do, very specific numerical algorithms. And what we want to do is we want to make it look like this entire thing acts as one whole piece. And what I mean by act as one whole piece, what I mean is that if you understand how to use the ODE solver, because you say, when you use the ODE solver, you say abs_tol for the absolute tolerance, then when someone writes a thing over here where they say, okay, in SciML expectations for uncertainty quantification, I want to have an absolute tolerance, that better be the exact same keyword argument, and we should actually use the same piece of code to be able to validate that our keyword arguments are doing the same thing, so our error messages should look the same, and everything across this organization, when you do ordinary differential equations or linear solvers or quasi-Monte Carlo simulations, or all of those should have exactly the same arguments, the same argument orders, and we should make sure that everything works as a cohesive system, so that we can compose it every way you want. And that's the SciML organization. And so the first timeline slide of many is, here's a simplified timeline of the SciML organization. And it kind of follows my own timeline of myself over the last 10 years, right? So the first versions of everything that we're having in DifferentialEquations.jl, it actually started as MATLAB plus C code that was written to target Xeon Phi accelerators. So we have a very long history of we want to use do parallel computation, whatever the fastest device is out there, even if it's a weird device, right? This got formed into JuliaDifferential and DifferentialEquations.jl, and so a lot of the timeline of the SciML organization was around numerical differential equation solvers. And I think a lot of people who knew us in our earlier stages, you know us as like, this is the DifferentialEquations.jl guys, right? But that kind of grew over time. So by about 2019, I took up a position at MIT in the Julia lab, and that was kind of a transition point for the SciML organization, because that was this point where we could start getting our own grant funding, where you start to write a whole bunch of grants and be able to say, now we get a whole lab of folks. It's not just a few folks unfunded, but now it's 20 students at MIT. What can we do with this power? And we really expanded the domain from saying we solve differential equations to we do numerical modeling and simulation with machine learning embedded. And that's a huge jump, right? to go from saying we do Julia differential equation solvers, JuliaDifferential, we rename ourselves in 2020 to say we now do this entire domain of everything that you want to do with modeling, machine learning integrated with modeling and simulation means, we should take on differential equation solvers, but we should also do nonlinear solvers, linear solvers, numerical optimization, And so we had this huge expansion that happened around that 2020 timeframe. And we've also had an expansion, a large number of folks that work with us and the maintainer groups and then the groups involved. And so that was really kind of this inflection point. And that's when we renamed to SciML, right? And we've been SciML ever since. Well, that means that in 2020, after this inflection point, we really had the goal over the next few years was, well, we need to get other solvers to that level that differential equations is at. And what do I mean by that? Well, things like linear solvers, things like nonlinear solvers, integrals.jl, like all these other pieces where you say, oh, these are other types of mathematical models. Those need to get to the level of DifferentialEquations.jl as well if we want to cover all these domains. And so from the 2020 to 2023 timeframe, we had to start up all these new packages to really hit to that level. And I'll go into more detail about that phase, because we're kind of now getting beyond that phase to the next phase of integrating then symbolic tools and everything that's going on with symbolic numerics and modeling toolkit as this kind of next stage of the organization. So that's like a very simplified timeline of, one day we were just numerical differential equations, then we're everything numerical solving, and then numerical solving with symbolics. But it's been a very long journey to be getting there, right? And then where are we going next? Well, we're just continuing to grow as not just, in terms of the code that we're writing, but also an organization, right? So we've launched this year the SciML Small Grants Program. So we have folks all around the world who are participating in, signing up to be able to take small parts of the project, and they get bounties for what they're working on. And we can use this to be able to incentivize and grow and get more new maintainers. And then we also have a lot of things that we're rolling out in terms of targeting static compilation and really making sure we can work with embedded devices, right? Again, we started very early on as, we work on, new algorithms, new math, and get new solvers. But at this point now we're saying, we're growing the organization, getting a lot of new people involved, but we're also working a lot towards getting embedded devices, getting into the work that's required to be able to put, the code that we have onto airplanes, cars, and all these industrial devices. And one of the big things that's really shifting as well is that there's a lot more going on in terms of the partial differential equation framework, which I'm not going to discuss within this talk, which I know a lot of people are going to ask about. But there's a lot of things in this 2025, 2026 timeframe about more integrations between the things going on in SciML and a lot of finite element tools and a lot of the tools for finite volume and all of that, and there's things I won't even mention as well, like WebAssembly. But that's like, in a nutshell, this is the timeline of the SciML. And so I'm going to go case by case into different domains and really highlight what this timeline looks like in very specific spots. Before I do that, I want to establish a ground on which we can kind of talk about all these places with the maturity level, right? And so we kind of think about our libraries as different, there's with hundreds of repos, you kind of have to say they're not all at the same maturity level. There's high maturity, which means these are battle hardened, and we know a lot of industrial users using it already. For example, DifferentialEquations.jl. There's the if most things that you look at and you run into with DifferentialEquations.jl, there's been 100 other people who have already looked at that, and then there's already a test case about that, et cetera, et cetera. So for most cases, when someone runs into an issue with DifferentialEquations.jl, I can just ask a question of, are you sure your model's okay? And they'll come back the next day and they say, yeah, the solver was right, my model was wrong, right? Like that's, but not everything in the organization is at our differential equation solvers of maturity, right? You have some things with medium maturity, which is that they have this feature completeness, but they have not necessarily hit the level of having the full testing across a huge code base and then integrated with hundreds of other packages. There are some that are in the low maturity level, which is that they're still heavily in development. Now, everything that is there is tested and tried to be maintained as well as possible, but its feature set might be not as good. Right? Might not be as complete. And then there's the research libraries, which again, we have a lot of research that's going on with a lot of new algorithms from the MIT side. And so those are kind of sectioned off, but they're still interacting with everything SciML because a lot of the research and new methods that we do, we don't want to just, write a paper about, hey, here's a new method that in theory could be fast. We want to say any new method that we come up with, it should be tested on real-world models to be able to say it is this much times faster than the current fastest algorithm, right? And this is why we integrate with, we don't just have the Julia code in here. We have wrappers over all the C libraries, over all the Fortran libraries and everything, because we want to be able to actually know if we say that something's fast, is it actually fast against some of these other standards, right? And so first I want to talk about our numerical solvers, right? So an incomplete list of numerical solvers that we cover are things like linear solves, nonlinear solves, differential equations, integrals, and optimization. Again, this is leaving off some other pieces like partial differential equations and a lot of other numerical tools like exponential utilities, quasi-Monte Carlo, and these libraries that are lower level utilities, right? And first things first, I think a lot of people, again, our background started with differential equations. So the first timeline that we should give on, what are we doing right now and what is improving is let's start with differential equations, right? So in 2016, that's when differential equations really started, and it really was hitting these features of, high performance, type generic, and with a robust event handling system that was kind of expansive, right? It really came out right out of the gates with saying, this is the expanded feature space that we want to support with differential equations, and this is how the next generation differential equation solver should work, right? When we came out with that in 2016, we really just had a bunch of methods for non-stiff equations and Rosenbrock methods for smaller stiff equations, right? Over the next 2 years of the organization, we then worked to build up a lot of the tooling for methods for larger scale stiff differential equations, right? And then, by 2019, we started doing things like automated sparsity support, so that way you can look at your code, automatically find what the sparsity of the Jacobian would be. By 2021, 2022, we started hitting this point of, now we're able to outperform sundials and be able to really be actually the fastest for these larger scale operations, and with the standard methods, right? So what have we been doing since we hit that benchmark in 2022? Well, we've been doing a lot of alternative methods that use alternative ways to get more performance. So one case has been these parallel extrapolation methods. So these are methods that, even though an ODE is something that's sequential, you can actually do different time steps all at the same time, and then you merge them all together. And if you do that with parallelism, you can get even more performance for ODEs up to size 200. And there's a lot of new solvers that we're developing along those lines. So that way, if you're in that range of 10,000 ODEs or less, there's a lot more performance we can get out. So that's kind of been a lot of this work since 2022 or so. And in 2023, we had, of course, the new GPU methods that were able to, they were about 1,000 times faster than our previous version of the GPU methods, and it was about 20x to 100x faster than what you see in PyTorch and JAX, because it was using a kernel generation approach instead of an array-based approach. So like these last few years have been kind of going more into that area of how can we use parallelism effectively to go beyond all the differential equation solver algorithms that you see, from before. So, the first 5-6 years was what kind of optimization should we be doing on the things that exist, and then it's new algorithms that can exploit more parallelism, because every computer that you run into has multiple cores, but most algorithms for ODs are not multi-core, right? So then what does that mean about our future? Well, in the near future, what we're doing is a lot of major performance improvements, again, on implicit methods for stiff solvers, right? This includes things like integrating NonlinearSolve.jl, right? We spent a lot of time on getting these new nonlinear solvers together, integrating that into the ordinary DifferentialEquations.jl framework instead of having it have a separate nonlinear solver will mean that things like line searches and trust region methods can be used within the stiff ODE solvers. And there's a lot of performance advantages we'll get there. Also, from the 2025 timeframe onwards, we have some research projects in new explicit ODE solvers. I'm not going to tell you how, but I think that we should get about 2x to 6x faster than the current explicit ODE methods that we have. And you say, but explicit ODE methods that were done in the 70s, no, we have it a whole way that we're going to do this differently. So, but that's been in progress for the last so many years. So, and then also making sure that we expand the package so that way all the code that we have, most of it is, we generally make sure that it's type stable and that it is non-allocating, but what we're going to be doing over the next year is making it so that way, we actually have proofs of non-allocating and proofs of static compilability, so that way we can just ensure that if you use anything within the ordinary diffie package, that it can statically compile for these embedded applications. Because again, that's kind of this real-world approach and this real-world kind of problem that we've really been focusing on. So we're talking a lot with groups that do things like industrial robotics, and this is really a area that we're targeting. There is something to mention. That is, there are plans for an ordinary DiffyQ v7 and that's probably only like 2-3 months away. So what would be the breaking change here? Well, the breaking change is that most algorithms that most of you don't use will not be imported by default. and that's the way to say it. I mean, because if you think what's actually happened to the differential equation solver is it's actually 10 megabytes of code, right? Like I'm not talking about like I compile it and everything. I mean, like if you look at the files for ordinary DiffyQ, there are so many ODE solvers inside of there that just the files themselves are 10 megabytes. It's in the order of a few million lines, and this comes down to the fact that you have these tableaus for Rackauckas, Chevy methods, and you don't need to know about all that. But literally, the size of our ordinary of the repo is about the size that a lot of people generate code to, right? Why is it like that? Well, we just have hundreds and hundreds of methods, and then most people only use 10 methods. And so what is the reason why ordinary DiffyQ takes a while to load? Well, it's because we load all those methods. So we should take a lot of those methods and move them out to different modules, so that way you don't install them by default. And this is actually something that takes a lot of time. It takes a lot of time to move a few million lines of code. But we are almost done with that. And so there will be this breaking change in the near future where if you happen to be using something like implicit Euler-Berry-centric extrapolation methods, then you need to do using ordinary DiffyQ implicit extrapolation. But the standard methods will still work. It just means that if you're doing one of these very specific methods for a type of PDE and you found like, oh, this thing is actually really fast for my type of problem, you will now need to load that solver, that specific solver. We're not going to load every single solver by default. So so there is a plan for a breaking change, but again, we actually don't make very many breaking changes. I'll give another talk in the near future, or almost right after this, about our development processes. Our development processes on downstream development means that if you make a breaking change, you have to go to make a PR to all downstream to every single repo that is using this piece of code to tell them how they should be updating things, and that kind of forces our developers to never want to make a breaking change, right? Because we have all these downstream tests and everything that try to ensure this, and this means that if you actually go to the tutorials that we made in 2018 on the differential equation solvers, you go to that YouTube tutorial that we made in 2018, you take that code, that tutorial still runs today. The only difference is actually that was back when Julia was in Julia 0.6. Julia was not at 1.0 yet. So there are some syntactic changes you have to do because Julia, the base libraries actually changed. But the ordinary differential equation interface is exactly the same. So this is actually going to be the first major breaking change that we've done in a while. But even then, it should only change code for people who are doing something weird. I like it when you're doing something weird, but that's how it has to be. I'm way behind on time. So, okay, simplified timeline for other core solver packages. So again, the differential equations where we started, but then a lot of what happened was we realized that, oh, hey, there's roots.jl, and for implicit methods, we use NonlinearSolve.jl. But over time, we started to see that, things like NonlinearSolve were not up to the SciML standards. And what do I mean by the SciML standards? Well, we start to say, well, we have, we want to be able to support every linear solver. When you work on GPU, it's an auto GPU. We want to have automated stiffness detection, and we want to be able to do things like if you have a sparse matrix, if you have, you don't have to tell me what the sparsity of your problem is. We'll automatically detect the sparsity of your Jacobian on all this. And a lot of these other tools in the ecosystem did not reach all those features, right? So we started off by using things like roots.jl and NonlinearSolve.jl, but over time we started to say, well, we want our own different linear solver interface, so LinearSolve.jl. Well, we need to be able to do more things with nonlinear solvers, so we drop NLSolve and we start to have NonlinearSolve.jl. And so all these kind of pieces have been built up over time, and a lot of them started in the year 2020. They took about 2-3 years to bake, and so now in about 2023, I think we can start to say LinearSolve.jl, NonlinearSolve.jl, and integrals.jl. These things have all kind of met their maturity level, right? In the 2020 timeframe, I think that some people here might have adopted things right out of the gate where they go, oh, this is cool and new, but it really has now taken the time so that we could say, okay, it has the features that we want. It has native solvers. We have benchmarks on the native solvers. The benchmarks on the native solvers say the things that we've created within LinearSolve and NonlinearSolve, they're faster than the things that we were wrapping in the first place. So you can stick to the whole Julia code and have the functionality, and you are good, right? we are there for NonlinearSolve.jl and LinearSolve.jl. And we are there in a sense for integrals.jl because a lot of the native Julia tools for integration do well. And so we've done quite well in those core solver packages. For time reasons, I'll skip over a few things more on the timeline there. I do want to mention, though, that there is one piece in the story of the numerical solvers which is not quite up to speed with some of the others, and that is optimization.jl, right? So optimization.jl, we kind of got late into optimization. You see that this actually started in 2017 or so. And the reason is because Julia has a lot of really good nonlinear optimization tools. So for a long time, we just said, optimization, that's a space of jump, and we don't need to touch it at all, right? And then we started to say, well, okay, there's so many packages for doing global optimization. There's NLOpt, evolutionary.jl, metaheuristics.jl, blackboxoptim.jl. So let's create an optimization package which is over all of the global optimization packages. So we called it galacticoptim.jl. It's like, more than global, it's galactic, right? And so we're just like, yeah, this is just for this one space, right? And then it started to say like, we also need to do local optimization, and sometimes we need to use optim.jl because it's BFGS, and sometimes we have to mix that with neural network methods like Atom and such. So let's start to piece those together. And what we started to realize was that we're just writing we're also in the game of nonlinear optimization, right? And so that's when it was renamed to optimization.jl. And so this was only done in like 2021, 2022. And we connected to the JUMP ecosystem so that way we can have all those available tools. But really then we're going into 2023 and saying, yeah, we need to really take this nonlinear optimization space seriously. And so all the things that we do in the differential equation solver is saying, we have automated, sparsity detection. Well, we should be able to do automated sparse Hessian detection, have our own algorithms, not just algorithms that are wrapping these C codes for, NLOpt, but we should have our own implementations of BFGS so that way they can be natively GPU compatible. All of those same things needs to then come into play for the optimization space. And so that's really ongoing, and we really want to get optimization.jl to be the level of DifferentialEquations.jl. And it's definitely not there yet, but it is one of the core pieces that we'll be doing in the near future. And yeah, I'm going to need to give like 8 of these talks. So there's also everything to say about modeling toolkit.jl, right? Which started much later in the system, but we had some very early versions of symbolic interfaces, and then through the time now we've really been spending most of the time trying to get up to, can we make it so that way we can automate the process of solving a DAE effectively and stably? And about 2022 timeframe, we're able to say, yes, solving a DAE, we can transform it into something that is good and stable. And now we need to work on scalability, right? And so the next 2 years were just the scalability problem with JuliaSim compiler. So that way all the things that we do symbolically, we can generate code that scales to the hundreds of thousands of equations. And Yingbo has been really hard at work on that, and he really has solved that problem. And so the next thing is, how do we make it so that way the entire organization can use symbolic numerics effectively? This is all the work on the symbolic indexing interface, and then also the things about integrating partial differential equations into this world, because right now everyone who's doing partial differential equations does not use the symbolic interface. They go directly to the numerical solvers, and so they lose on all the symbolic optimizations. But that was because we couldn't scale the symbolic interfaces until very recently, but now there's a whole lot of work to make sure that all the PDE things actually can use the symbolic interface. And so that's going to be a lot of this work going on in the near future. I'm not going to be able to talk about, these are some of the slides that I have from Yingbo on, how we can take very large models and then regenerate loops on them and be able to optimize them automatically. Folks that are interested in things like loop vectorization.jl, the guys who work on loop vectorization.jl are the ones who have been building all the symbolic compiler tooling as well. So so there's a lot of nice stuff baked in there. Yeah, and I'm going to be running out of time. So I get to again, there's a SciML talk, but in half an hour we can't even get to anything on machine learning. But I think that one of the things I want to point out is that a lot of the integration with differentiable programming, we've been working on many different methods for how you differentiate solvers over the years. We recently put out this review with some of the folks in the audience here, and it really goes into a review of, here are the 20 different ways that you can differentiate solvers, and here here's how they work, here's the different scaling, here's the trade-offs between them and all. And so we've really started to take the effort to be able to write down how all of this works. And yeah, so I'm going to be running out of time. So what was skipped? Well, everything that was in my slides. And then I also didn't even go into anything like SciML PDE solvers, jump processes, uncertain quantification. I think the point to get across with this talk is that the state of SciML is the thing is just huge now. And there's a lot of things going on. So I wrote down these slides, and it was basically like, oh, what are the ongoing projects in the organization? And it was a list of 100 things because we have over 100 contributors, right? And so, yeah, for more, we'll have to have follow-up discussions, and there's a lot going on. I'd love to talk with anyone about what you think is the most important. We'll have a birds of feather tomorrow, which is where you get to brush me about, like, oh, I thought, are we going to work on this? Are we going to work on this? We're working on everything. So thank you very much.